Что? Подслушивающая аппаратура. Ну да. Okay, so this is a continuation of my quantum groups lectures from last week. So today the announced topic was Yangians, but we are not there yet. So actually Yangians probably will appear tomorrow. So let me, so what I want to talk about, I didn't even explain how to construct quantizations of ordinary finite dimensional simple Lie algebras G. So let us start with that. We armed ourselves with a powerful notion of quantum double and the corresponding categorical notion of Drinfeld center of a monoidal category. This allows you to construct quantum groups corresponding to finite dimensional simple Lie algebras and more general for any Kac-Moody algebra. And it moreover constructs it not just by itself, but also with an important structural ingredient, which is called the universal R matrix. So let us start with the simple example of SL2. I just gave you the definition without any motivation, and then wrote some mysterious formula of Drinfeld for the R matrix. But how do you come up with such a formula, actually? Well, so let's look at the, so we have a simple Lie algebra, and it decomposes into positive nilpotent subalgebra, Cartan subalgebra, negative nilpotent subalgebra. And I'm going to consider the example of SL2, and then this is spanned by E, this is spanned by H, and this is spanned by F. Now this thing is called B+. This is the positive Borel subalgebra, and this is B-. This is the negative Borel subalgebra. So the way you construct UQ of G is you start off with the half, which is UQ of B+. And in the SL2 case, this is something very simple. So UQ of B+, I remind you, it's generated by K and E, where K, E K inverse equals to Q squared times E. And also K is a group-like element, while E is a skew primitive element. So it is almost the same as a primitive element, except to account for the non-commutativity of the coproduct. So E tensor K plus 1 tensor E. Actually, maybe I should mention that these skew primitive elements are important because if you look at the dual picture, namely comodules, then group-like elements correspond to one-dimensional comodules, and skew primitive elements correspond to X1 between one-dimensional comodules. So this represents a class in X1 between K and the trivial comodule. So it's natural to consider them. And let me, I'm going to want to take duals, so let me start with the situation with roots of unity. So let's say that Q is the root of unity. So order of Q is going to be L. And in this case, I told you that we have a Hopf ideal generated by K to the L minus 1 and E to the L. So this is a Hopf ideal. Let me call it I, so which I remind you means that delta I is contained in I tensor H plus H tensor I. So this is our H. And then you can form the quotient H over I. This is the small quantum group UQ of B+. And this is the algebra that appeared in a problem set. It's called the Taft algebra. It has dimension L squared. So it has a basis k to the I, e to the j, where I and j are between 0 and L minus 1. And it's generated by a group-like element of order L and skew primitive element of nilpotency order L. So this is the simplest Hopf algebra you can imagine, which is not co-commutative. And then let's look at what happens if we take its quantum double. So you can compute that. So this is going to be a tensor product as a vector space and even as a co-algebra. It's a tensor product of this thing with its dual. Well, you have to oppose the coproduct on the second part. But a fact is that this Hopf algebra is self-dual. So the dual Hopf algebra is basically isomorphic to it, up to changing the coproduct. To the opposite, well, basically because there are very few Hopf algebras with this structure, so there is not much room for variation. So, so a fact is that UQ of B plus is self-dual. And so, so I want to write this as a product of two copies of UQ of B plus, but actually I want to make a G, so I'm going to write one of them as UQ of B minus. Remember, this is only as a co-algebra and not as an algebra, so these things don't commute. And UQ of B minus is going to be generated, so it doesn't matter, it's just a matter of convenience, and it's generated by K and F such that we write the relations. So KF K inverse equals to Q to the minus 2F, and delta K equals to K tensor K. And delta F is equal to F tensor 1 plus K inverse tensor F. It's really the same thing as this thing above. Because, well, here you have Q squared, here you have Q minus 2, but this can be achieved by replacing K with K inverse. And similarly, here we have K inverse on the right instead of K on the left. But again, if you replace F by KF, you go from one to the other. So, so we've got this tensor product. So the main commutation relation, so the proposition that I told you that these things don't commute. The main commutation relation turns out to be, so now we want to identify, so there is a K here, and there is a, let's call it K plus, and there is a K here, let's call it K minus. And let me, yeah, K to the L minus 1. F to the L equals 0. So we have this K plus here and K minus here, and I want to, so it turns out that K plus K minus inverse is a central element. Well, that's clear because it commutes. So it turns out that this K and this K have the same relations with E. So K plus and K minus have the same commutation relations with E. So this element is central. Let me call it C. And let me take this double of UQ of B plus. You see, this thing has it's too big. It has dimension L to the fourth. But I want to construct an algebra of dimension L cubed. So I want to kill something. And so what I kill is C equal to 1, so this relation. So this identifies these two Ks. So this will be just denoted by K. And then we will have only one K. And then what you can check, that's a nice calculation, really enjoyable, is to show that commutator of E and F in this algebra, I told you they don't commute, so it tells you exactly what the commutator is. It's K minus K inverse divided by Q minus Q inverse. And so we get, so what we get is that the double of UQ of B plus modulo this relation C equals to 1 is actually exactly this small quantum group UPU of SL2, UPU of G, that we defined in the previous lectures. And in fact, you can say more than that. You can say that this is really a split extension in the sense that double of, this pen is not so good. Double of UQ of B plus is equal to UQ small quantum group UQ of G tensor product with the group algebra of Z mod L, which is generated by this element C. If L is odd, so we will considering the case when L is odd. When L is even, things are a little bit more complicated, but essentially this is what happens. And so this gives you a conceptual construction. You don't have to guess this relation. You simply get it for free. And also what's more important is we know that the quantum double is a quasi-triangular Hopf algebra. It has an R matrix. And we have the R matrix. So let's try to compute this R matrix. So the R matrix of the double is supposed to be the sum of AI tensored with AI star, where this is a basis of H, and this is the dual basis of H star. What we really need to do to compute this thing is we need to see what is the pairing between UQ of B plus and UQ of B minus. And you can compute this pairing. So UQ of B plus cross UQ of B minus to C goes like this. So K to the I with K to the J gives you something like Q to the 2ij. And then E with F equals to 1 over Q minus Q inverse. So why did I write just E with F? Of course, you have many other elements. But you see this is a Hopf pairing. It defines an isomorphism between this Hopf algebra and the dual of this one. So this is what is called Hopf pairing. So which means that it's, in terms of this pairing, what it satisfies the following condition, that delta x with y tensor z equals to x with yz. And the permuted one satisfies the same. So y tensor z with delta of x equals to yz with x. And using this, you can reduce to computing the inner product of generators. So in fact, it would be enough to say that k with k is q squared, and E with f is 1 over q minus q inverse. And of course, k with E. So this is supposed to be homogeneous of degree 0 with respect to the weight decomposition. So this is going to be 0, and also ek, and the same thing for f. OK, and so then what you can compute, it's a nice exercise to compute what is going to be e to the n with f to the n. And what you can get is, so you will get n factorial, but it will be a q factorial. And there will be this thing to raise to n power. So it's going to be divided by q minus q inverse to the n. And so, and what this will give you is the following thing. So the R matrix is going to be R0, which lies in the Cartan, which lies in this K subgroup. It does. This is just 1 for n equals 1. And this is. So there will be some kind of diagonal part. And then maybe I should write it on another board, because it's too low. So we got R. So you have to incorporate this pairing. And and this is what I wrote as q to the h tensor h over 2. May have forgotten the 2, but it needs to be there. So this is really what accounts for this. It's a kind of trivial part. And then there is a part that corresponds to those things. So we just need to sum e to the n tensor f to the n and divide by their inner product. So we will get the sum over n greater or equal to 0, e to the n tensor f to the n, and divide by the inner product. So this is going to be q minus q inverse to the n divided by n q factorial. Actually, I forgot to write a factor here, which is q to the n times n minus 1 over 2, which needs to be here. And so it also will be here. And so this is the Drinfeld formula. So you don't need to guess this formula or check that it satisfies Young-Baxter equation, which is a rather difficult calculation, if you do it directly, because this all comes from the theory of monoidal categories and Drinfeld center. Could be. Well, it depends. I mean, I don't remember. Maybe it is minus. It depends on the conventions for the coproduct and the. So it's. Okay. No, if I put it with plus here, okay, maybe it's minus here and plus here, because the formula of Drinfeld is with plus. Okay, so this is the Drinfeld formula. And now I want to generalize this to an arbitrary simple Lie algebra. So because of, before that, any questions about this? Oh, these coproduct formulas? No, so this is a kind of the most natural thing you can do if you want to make things non-commutative. So if you have a Lie algebra, this is basically, remember that we have k, which is q to the h. So this is equivalent to saying, so we had k equals to q to the h. So the first relation is just equivalent to saying that h bracket e equals to 2e, which is in the usual positive part of SL2. And actually, the only thing we change is the coproduct formula for E. Instead of writing E tensor 1 plus 1 tensor E, we write E tensor K plus 1 tensor E. So this is the simplest way in which you can make the coproduct non-co-commutative. Because if you have a commutative or co-commutative algebra, then you are in the world of usual classical groups or Lie algebras. Essentially, yeah. Okay. So now, other questions? So now I will explain what happens for general G. And the formulas will get more complicated, but the story will be completely parallel. So a general simple Lie algebra G has a... OK, so maybe I should first remark, well, I did it for roots of unity. And if... similarly, for generic Q, but with completions. So what will happen for generic Q is that we will not have the relations that k to the L equals 1 and e to the L equals 0. So this algebra will be infinite dimensional, and so this algebra will be topological, and we can replace it by but it is graded, and we can kind of replace it by its restricted dual, and also we have to be careful about what happens to those k's, but this is kind of a trivial business, and so basically. You can define some kind of restricted quantum double, which will be a product like that with some funny multiplication. And then you quotient it by c equals 1, and you will still have this relation, and you will still get the quantum SL2. So as long as you are careful with completions here and take a restricted version of this product, you will get the usual quantum SL2. However, because we took the restricted product, the R matrix is not going to lie in this tensor product. It will in the tensor product of this algebra with itself. Because it is given by the infinite sum, it actually will be in the completion of the tensor product. So the only change is that the R matrix, so this is the sum from n equals 0 to L minus 1. because it gets truncated at L, because these things are 0. And the only thing is that R is the sum, is this Cartan part times the sum from n equals 0 to infinity of the same things. So this is an infinite sum. And what it leads to a situation when the category of, so we know that if we have an R matrix, then the category of representations is a braided tensor category, where the braiding is defined by the R matrix. So the category of all representations will not be a braided tensor category. Because if you try to evaluate this R on the tensor product of two arbitrary representations, then this series will not converge in any reasonable sense. However, we don't care about arbitrary representations. We care usually about some nice representations, such as finite dimensional or category O. But if V and W are locally nilpotent, under E, which means that for every vector V, there exists n such that e to the n times v equals 0, which includes finite dimensional representations and representations from category O, then R restricted to the tensor product of such representation makes sense. Because if we apply this sum to an arbitrary product of vectors V tensor W, because of this local nilpotency condition, this sum will terminate and become finite. Makes sense. And maybe we should, So maybe we should, So in such a representation, automatically we'll have that H is going to be locally finite, and or K will be locally finite. So such representations form a braided tensor category, and in particular finite dimensional ones, which is the important thing. Well, no, I mean, it's if you are very insistent, you can actually make more, a bigger category of representations. You can define some kind of, you can try to sum this series in the sense of analysis or something like that. So there are possibilities for that. Anyway, but I don't want to get into this business, and I want to explain what you do for higher for other Lie algebras. So general G. So for general G, semi-simple or yeah, I mean you can make sense of it. Yeah, it's but you have to. But it's more. Huh? Yeah, well, first of all, it converges if you use formal Q, which means Q is exponential of H bar, and H bar is a formal parameter. Then it converges then it makes sense for any representations, just for trivial reasons. But more interestingly, if you take something like principal series and try to make sense, you will get some series, and then you can try to make sense of it in this sense of analysis, and you can do it, and it's very interesting actually. But it's kind of beyond the scope of this lecture. Huh? What? Yeah. So there are some subtlety. Yeah, but okay. So general G, what the main combinatorial input is the Cartan matrix, and this is a matrix which has 2's on the diagonals and negative numbers of the diagonals or 0, and it is symmetrizable. So there are some numbers di such that di times aij is dj times aji. And for simple Lie algebras, these numbers are either all 1 or 1 and 2 or 1 and 3. And then you have, for each of them, So simple Lie algebra is generated by a bunch of SL2s, one for each index I. And similarly, quantum group will also be generated by UQs SL2 for each index I, except that the Qs for different i's will be different. Namely, we will have Qi equals to Q to the di. And then, so UQ of B plus will be generated. So you first define the UQ of B plus tilde, which is a kind of free product. So you take UQ of BI, well, let's do B1 star UQ R of BR UQ1 of B, maybe, let me write SL2 plus. This is the positive part of SL2. SL2 plus, but with different Qs. And what this means is that it's generated by Ki and Ei with relations, with SL2 relations, and also relation that Ki commutes with Kj. You don't impose any relations on the EIs. So you get, in particular, the subalgebra generated by the EIs is going to be just free, non-commutative algebra. And then what you can do is you can kill, so this is kind of generic Q construction. So UQ of B plus is the quotient of this by a certain ideal I, and this I is the largest Hopf ideal, which does not contain, not containing EI for any I. So we do not want to kill the generator's EI, because then our rank will get reduced and we will not be deforming the original Lie algebra, but some Lie subalgebra only. But otherwise, we want to kill everything we can kill to make it smaller, because free algebra is kind of too big. And then, so a theorem, so if you do this for Q equals 1, which means you work with the usual algebra, then it is known, it is a theorem of Gaber and Katz, that what you kill is exactly the Serre relations. And it turns out that here you also kill exactly the Serre relations, except the Serre relations get Q deformed. So theorem, I guess, maybe Lustig, says that I is generated by Serre relations. And the Serre relations look like this. So usual Serre relations look like this. You take the sum from k equals 0 to 1 minus aij. And then you take binomial coefficient, 1 minus aij, choose k, e to the ei to the k, ej, and ei to the 1 minus aij minus k equal to 0. And here, what you should do is just take the q binomial coefficient, which is the corresponding ratio of q factorials. No, but I mean, you have, maybe I forgot to say, there is also another relation that I forgot to write. So there is a relation ki ej, ki inverse equals to ai, q to the ai, so qi to the aij, ej. And so this is how it. Okay, so this is how you construct this thing, this half. And then Uh, in the set relation, yes, Qi, thank you. But in the simply list case, the Qi's are all equal to Q. And then, so you need to repeat the same story. No, I impose it already in the definition of this free algebra. And then I look at the remaining relations. Okay, and so now you do the same procedure. So you take the double of this thing and some restricted in some sense. So this is going to be the product of uq of b plus with uq of b minus. So we have a similar kind of pairing here. And the main relation in this pairing will be ei with fj. Inner product will be 1 over qi minus qi inverse times delta ij. So using this relation, so this is called the Drinfeld inner product. And using this inner product, you can identify the dual of this Hopf algebra with the same kind of Hopf algebra with b minus. And then you get that this is really as an Hopf algebra. If you take C I, which is ki plus times ki minus inverse, then if you take the double of this uq of b plus and mod out by ci equal to 1, which are central elements actually, what you get is just uq of g. Restricted means if I'm not at root of unity, then strictly speaking, the dual of this is not equal to this, because the dual of this has some topology of the dual space. So you're supposed to take some subset there, which looks like this.
And what was the meaning? So over here we had like this group algebra of Z mod L. In this side, what's the meaning of that Z mod L in terms of the Cartan? Like it's some sort of
Well, it is, yeah, it's for the root of unity, it is the points of order L in the maximal torus. And there will be a similar decomposition here at roots of unity. And if you're not at roots of unity, this decomposition is a little bit, you have to be careful, but essentially you have a decomposition like that as well. Yeah. I will say about that. So a comment that I want to make, so you still get a formula for the R matrix, which is going to be the same thing. But in this case, there is no such simple basis, like k to the I, e to the j. So this sum a priori is not so simple. But there is a way to use, there is a nice basis, which is called the PBW basis, in which you can write this formula. And then it is written as a product over all roots. So this is a formula of Horoshkin and Tolstoy, so or maybe Lewandowski and Soibelman. So this is a really nice formula, but to derive this formula, we need to discuss braid group action, which I didn't have time to talk about last time, so I will skip this. But you can obtain a nice formula even for an arbitrary G. And also, I want to say what happens at roots of unity. Well, again, things get more complicated because what happened, remember, roots of unity were a generalization of characteristic P. And in characteristic P, we need to impose, to get the restricted enveloping algebra, we need to impose the relations not just ei to the p equals 0, but also for all roots, not necessarily simple roots. We have to impose the condition that the pth power of the corresponding root vector is 0. And so the question is, what is the Q analog of a non-simple root vector E alpha? And that's not such a simple question. So actually, this question can be resolved using so-called braid group action of Lustig on the quantum group. So of course, enveloping algebra carries a natural action of the Weil group, or rather some extension of the Weil group, called Tits extension by Z mod 2 to the power rank, basically by conjugation. And this action doesn't nicely lift to the quantum group. But what lifts to the quantum group is the corresponding action of the braid group, which is a covering group for that Tits extension. And then you can act with those braid group elements on these generators EI and obtain some root elements, which are called Cartan-Weil bases, and which is kind of a basis of the underlying quantum Lie algebra, although the quantum Lie algebra doesn't literally make sense, but you get something like that. And this allows you to define these elements, and then you put such relations, and you get the small quantum group. So I cannot, this is a big story, so I cannot really talk about it. So that's an explicit description. And we still have this picture, which we had in SL2 case, namely we have Katz-de Concini quantum group. So for root of unity. And so this maps into the small quantum group by quotienting these relations. And this embeds into the Lustig quantum group, which is obtained by introducing divided powers in a very similar way to what we did. And that maps back to the classical enveloping algebra. And this is called the quantum Frobenius. And this is a short exact sequence of Hopf algebras, which means that this thing is all killed. What? Order. Yeah. So there are some restrictions for the order of the root of unity. And so this was explained in Braverman's lectures, that sometimes you get G here, and sometimes you get the Langlands dual, depending on the order of the root of unity. Again, this is going to remain beyond the scope, but this is basically the picture. And finally, what I want to make a comment, that this all makes sense for any symmetrizable Katz-Moody algebra. So you can define the corresponding quantized algebra UQ of G, which is a quantum deformation of the classical Katz-Moody algebra. And this is going to matter to the story about quiver varieties if we reach that point, I guess, yeah? Which is unlikely, I suppose. Okay, so this is the story about these quantum groups. So the next thing I want to mention is so the formal version of things. So in physics, people often do perturbation theory for want of a better theory. And of course, theory of quantum groups is not an exception. So perturbative versions. And perturbative versions are just when you take Q equals to e to the h bar, or maybe e to the h bar over 2, where h bar, and you work over the formal power series in h bar. And in this case, what you get is, and you complete. So you not just take, so you define the algebras in the same way, but you complete, so there you can write down, I didn't write down the relations. So you can write down the relations. So you will have relations for e's, and similar relations for f's. And then you will have a relation which says the only linking relation that you will get is that EI with fj is going to be ki minus ki inverse over qi minus qi inverse times delta ij. Otherwise, it's just going to be a second copy. There will be the same relations for f's as for e's, including the Serre relation. And this relation comes from the definition of the quantum double. So if you do the same thing, but with, you say that ki equals to q. What? Delta ij. So, so you can say that ki is q to the hi, which is e to the h bar times hi over 2. And then you get what is called the quantum universal enveloping algebra. In the sense of Drinfeld, which is just a formal deformation of u of g. So actually that it is a flat deformation is a non-trivial statement which goes under the name of Poincaré-Birkhoff-Witt theorem for quantum groups. So this just means that you get a Hopf algebra over u over formal power series in h bar, and in the topological sense, because this is a topological ring, so everything is complete with respect to h-adic topology. In particular, when you take the tensor product of two spaces, you're supposed to complete it with respect to this topology. So in that sense, you have a Hopf algebra A over this ring, and then A over HA is identified with u of g. So just a formal deformation in the sense of formal deformation theory. And in this situation, of course, the coproduct in u of g is commutative. So if you have such a thing for some Lie algebra g, so now let's forget about simple Lie algebras and Kac-Moody algebra and just take any Lie algebra g. Then we can look at delta of x minus delta opposite of x. And when h equals 0, this is going to be 0. So this means that this is equal to big O of h bar. So we can take the limit when h bar goes to 0. So this means it lies in the maximal ideal generated by h bar. In the image of in the maximal ideal generated by h bar times your algebra. And so then you can take the limit in this algebraic sense of delta of x minus delta opposite of x over h bar. So this is called little delta of x. And this gives you a map from enveloping algebra of G to the tensor product of enveloping algebra of G with itself. So it really measures the first order failure of the coproduct of the quantum group to be co-commutative. And that's consistent with our story about quantization and passing from classical physics to quantum physics. So dually, if we take the dual, this will correspond to measuring the failure of the product to be commutative after deformation. And that's exactly what happens when you pass from classical mechanics to quantum mechanics. So this procedure is not just replacing a commutative algebra by non-commutative, but it's a kind of gradual deformation of commutative into non-commutative. And so the commutative algebra of observables in classical physics keeps a trace of this procedure, which is the Poisson bracket. So this thing is the dual to the Poisson bracket, so it's called the co-Poisson Hopf structure. And in particular, nice property of it is if you restrict it to G, which is the degree 1 elements here, then it actually maps G to G tensor G, and more precisely to wedge 2 of G. So this is a property of this map. And moreover, it satisfies some properties. So first of all, the co-associativity of the coproduct gives rise to the co-Jacobi identity for this. So here are the properties of this thing. So first of all, if you look at the dual of wedge 2 of G star into G star, then this is a Lie bracket, which means it satisfies Jacobi. And the second property is it's compatible to the bracket. It's a derivation. So delta is a derivation. Namely, it means the delta of the commutator xy is x tensor 1 plus 1 tensor x with delta of y plus delta of x y tensor 1 plus 1 tensor y. And the definition, such a pair, G delta, with these properties is called a Lie algebra. And it's called, so Drinfeld called it a Lie algebra because it has two Lie brackets. The G has a Lie bracket and G star has a Lie bracket. So you have two Lie algebras corresponding to the same space. One realized on the space itself and the other realized on the dual space. And this Lie algebra, it is called the quasi-classical limit of the Hopf algebra, so of A. So here is an exercise to compute this for quantum SL2. So you're supposed to get delta, and it's going to be delta of E. Well, up to signs, it's going to be E wedge with H. Delta of F is going to be F wedge with H. And delta of H is 0. And also A is called a quantization of this Lie algebra. So quasi-classical limit is a very simple procedure. It's basically taking the derivative. But quantization is more like integration, so it's more difficult. But also, what is worse, it's a very non-commutative kind of integration. So when you're given only the first order part of delta, and even only the anti-commutative part of it, you are supposed to reconstruct all the higher parts. And it's not obvious that this even exists, because at each step you are going to get some nonlinear equations, and who knows why they have solutions. So ordinary deformation theory, classical deformation theory, doesn't give an answer to that. And so, but nevertheless, it's true. So we proved that with David Kazdan about 25 years ago. So this is a theorem. Well, so what ordinary deformation theory says what? This is what was mentioned in Roman's talk, that if you have an algebra A, then infinitesimal first order deformations correspond to H2 of A with coefficients in A. Abstractions lie in H3. And so in particular, when H3 vanishes, then you can, any first order deformation lifts to the deformation of any order. But if H3 equals 0, is not equal to 0, then it's already tricky, because what you get abstractions. And you get abstractions at each step. And actually, you also get abstractions here. So what you have to do at each step, you have to resolve that. You have to make sure that cohomologic class of your abstraction vanishes. And it could be that you made a wrong choice, but because at each step when abstraction does vanish, then you get to make a choice in a certain tensor over H2. And if you make a wrong choice, an unfortunate choice at step 5, then at step 278, you may get stuck. And then you have to go back to step 5 and change your choice. Huh? Butter, what? Ah, yes. Anyway, so this is not the way to do it. And so this is one of those deformation theory problems that has a solution, but you can't prove it by classical deformation theory. And in fact, so the theorem with Kazhdan, which we proved, says that any Lie algebra has a quantization. Yeah, it's non-trivial. No, cohomology that's responsible is non-trivial. So it has a quantization over a field of characteristic 0. And in fact, we prove more. We prove that this quantization is given by a functor from the category of Lie algebras to the category of quantum enveloping algebras. And moreover, if you consider Lie algebras over formal power series rather than just over the ground field, then this functor is an equivalence of categories. So you can go back and forth. So in fact, it's given by a quantization functor. But this is one of those problems which cannot be solved by classical deformation theory, at least as of now. And you actually, even though it's true over Q, actually to prove this, you need complex analysis. You need, or you need some number theory. So you cannot really prove it algebraically over Q. So you need existence of Drinfeld associators. And so you need some analytic or number theoretic input, similarly to Kontsevich quantization of Poisson manifold, where you also need such an input. Well, I mean, certainly, like I say, if you have a Lie, it works if you take a Lie algebra over formal power series. So if you have a Lie algebra over the field, you can lift it arbitrarily over formal power series and then quantize. You will get a different quantization. But in the sense that it's an equivalence of categories, it is unique. So let's see. OK. So now I want to talk about the dual story. So, so I can look at the dual. So let's say G is a Lie algebra of G, which is G is an algebraic group. And then I can look at the dual of G, of UG, and let's take the finite dual, which means it's the linear functionals which generate a representation by action of UG on the left and on the right, which generates representation that integrates to the group. So let's say it's a connected group. So then this is simply function algebra on this group. Simply connected algebraic group. Well, and no, let's take, okay, so let's take not finite, but sub G, which means that representation that so is generated by elements such that when we act on this element on the left and on the right by our Lie algebra, it generates a representation of this group cross itself. So then it's just the functions on this group. So it's basically algebra of matrix elements. And so we get, by duality, what you get from that is you get a delta dual, and this maps this O of G, tensor product with O of G, to O of G. So it's easy to show that it actually preserves this O of G. And what you get, so this corresponds to and this is a Poisson bracket. So delta star of f g is f bracket g, and this is a Poisson bracket. Namely, the Jacobi identity comes from here, and this tells us that it's a derivation in each argument. And moreover, what you get is that the multiplication map from G cross G to G is a Poisson map. So there is a natural Poisson bracket on G cross G, which is a product of the bracket on G with itself. And this thing preserves this bracket. And such a structure is called a Poisson algebraic group. In a similar way, you can define Poisson Lie groups, Poisson formal groups. So such G with brackets is called a Poisson algebraic group. And maybe I should have said affine. So this is an affine algebraic group. And in a similar way, you can define Poisson Lie group, Poisson formal group. Poisson formal group will be obtained if we take the full dual instead of just this G part of the dual. Poisson Lie group just means that you have a Lie group with a Poisson bracket such that multiplication is a Poisson map. And so this can be viewed, so this story can be viewed as quantization of Poisson Lie groups. So this implies, so the theorem that I stated there implies another theorem with some additional work, not very much, that any Poisson group can be quantized in any of those three settings. Has a deformation quantization. So this means that I can deform the product. It's exactly what we want in this quantum classical versus quantum mechanical picture. So if you have any Poisson Lie group, then it admits its algebra of functions, admits a deformation to a Hopf algebra such that in first order the commutator recovers the Poisson bracket. And you can view all these quantizations UQ of G from that point of view. Okay, and then maybe let me say a couple of things about quasi-triangular structures. So what if you have so we work over formal power series in H, and you have this quantum universal enveloping algebra in the sense of Drinfeld, and suppose A over HA equals to enveloping algebra of G, and suppose A has an R matrix. So I remind you what this means. It means R times delta equals to delta opposite times R. And R delta tensor 1 of R equals to R13, R12, R23, and 1 tensor delta of R equals to R13, R12. So these are hexagon relations. And in this case, we require that R equals to 1 plus big O of H bar. So since the coproduct becomes co-commutative for U of G, but actually this is automatic. It follows. You cannot have an R matrix on U of G. So this will be automatically so. And in this case, you can take the first derivative. So 1 plus H bar little r plus O of H bar squared. So more precisely, well, this is a bad way of writing it. I mean, it would be a way of writing it if we trivialize this deformation, but the way you should write it is this. You take little r which is the limit when h goes to 0, big R minus 1 over h. And this nice property of this is R belongs to G tensor G. And then what properties does it satisfy? So it actually follows from these hexagon relations when you take the linear part. And then the co-bracket actually is expressed in terms of R by taking x tensor 1 plus 1 tensor x commutator with R. So this is a so I said that delta is a derivation, so which means that delta is a one cocycle of G with coefficients in wedge 2 of G. And this simply says that delta is a co-boundary of well, G of G, let me write it in G tensor G. And this simply says that this cocycle is a co-boundary. But moreover, recall that we have the quantum Young-Baxter equation. R12, R13, R23 equals to R23, R13, R12. And if you linearize this, so expand in a power series in H bar, then, well, the non-commutative, so this differs just by the order of factors. So in the linear order, you will get a tautological identity. And the only interesting information will start with H square order. And in H square order, you will get the following equation. Little R12 commutator with R13 plus R12 with R23 plus R13 with R23 equals to 0. And this is called the classical Young-Baxter equation. And finally, since this is skew-symmetric, the property of the R matrix you will get is that R plus R21, which is denoted by T, is a G invariant. And so, so I'm going to wrap up, but the definition that I will make is that a quasi-triangular structure on a Lie algebra G, so a quasi-triangular structure is the definition of Drinfeld on a Lie algebra G is an element R in G tensor G such that R plus R21 equals T is G invariant. This is normally called Casimir tensor, and R satisfies the classical Young-Baxter equation. And the theorem that we proved with Kazhdan is that any quasi-triangular Lie algebra can be quantized and the quantization is actually, as an algebra, is isomorphic to the undeformed algebra tensored with power series as algebras. So coproduct is certainly different. Here it's co-commutative, and here it is not. But the product is the same. But so in particular, the quantum group UQ of G, if you take formal Q, is isomorphic to U of G as an algebra for finite dimensional Lie algebra G. And this is not very hard to prove by classical deformation theory, because actually U of G has H2 of U of G with coefficients in U of G is 0 by Whitehead's theorem. But to construct a particular isomorphism is pretty difficult. Only recently, people were able to explicitly construct such isomorphism for SLN. And it still remains an open problem for other types. For Kac-Moody algebras, it's not really true, because in that case, this R lies in some completion. And in that case, this theorem doesn't apply. But nevertheless, you can prove that you obtain some quantization with an R matrix, which lies in some completion. So anyway, so this is the story with these quasi-triangular structures. And the triangular structure, which corresponds to symmetric tensor category, will be recovered if R is Q-symmetric. So triangular case corresponds just to the situation when T equals 0. This Casimir equals 0. So the reason this is nice is because, so maybe I'll talk about that at the beginning of next time, is that there is, so for Hopf algebras, we have a notion of quantum double. And similarly, we have a notion of classical Drinfeld double for Lie algebras. And this connects to the notion of Manin triple. And Manin triple is something that's very easy to construct, actually. And this is a way to construct a lot of Lie algebras, and by this theorem, a lot of Hopf algebras. And so Youngians and quantum affine algebras, well, quantum affine algebras we already defined because it is just these UQ of G for affine Lie algebras, but their limits, which are Youngians, can also be obtained by thinking about this quasi-classical picture, which is very useful. So this is why I spent some time talking about it. Okay, so thank you for today. The questions? Yeah. Well, in a sense, because so there is what you need for the quantization formula is you need a Drinfeld associator. And for Drinfeld associator, so there are various associators that you can construct by means of analysis. For example, one that comes from the Knizhnik-Zamolodchikov equation. And that one you can, yes, you can write some formulas. So you can write it as a sum of things, and the coefficients are certain integrals, some called multiple zeta values. So this is related to all kinds of graph business, but and so it connects to the Kontsevich story, where you also integrate things over some spaces corresponding to graphs. Analogy is very strong. You can Drinfeld. So Tamarkin showed that you can use a Drinfeld associator also to construct quantization of Poisson manifolds. And then it was shown later that so Kontsevich defines actually two quantizations, one real and one complex. And it is shown that complex quantization is obtained from the Knizhnik-Zamolodchikov associator, and real quantization is obtained from so-called Alexeyev-Tarasyan associator, which has real coefficients. But originally, Tamarkin actually used our theorem. In the original version of his paper, he used our theorem to prove Kontsevich theorem. That was 1 year after Kontsevich's paper. Well, I mean, what he used is universal version. So actually, there is a functor, and moreover, there is a morphism of props. So there is a prop of Lie algebras and prop of quantum enveloping algebras. And this says that they're just isomorphic. That there is an isomorphism between them. And he used that thing in some kind of universal Lie algebra to show that certain, so prove some statement in that theory which was needed to quantize. Huh? Product and permutation category. So a prop is kind of like an operad, but operad has operations which have many input and one output, and those generate everything. For prop, you can have operations that have any number of inputs and any number of outputs. For example, Hopf algebras are not algebras over any operad, but they are algebras over the prop of Hopf algebras because you have this thing. Short definition, it's a monoidal category generated by one object. Symmetric monoidal category generated by one object. So its objects are going to be positive integers. Amorphisms from K to L are operations which with K inputs and L outputs.
Just make a comment.
Mhm.
So if you are talking about this analogy between small quantum characteristic this situation, and I also mentioned in my talks, but this double construction is one place where it breaks completely because the restricted developing is not double.
Yeah, no, but I mean, you might ask, what does the double construction do in roots of unity? And what it doesn't produce the Concini-Katz quantum group, and it doesn't produce the Lustig quantum group. It produces some hybrid between the two. So it is going to be, like the E part is going to be Lustig, and the F part is going to be Katz-de-Concini. So that's actually also an important type of quantum group, which is in between of those two.
Some classification of quantum groups, thinking diagrams.
Well, I mean, the classification is the same if you talk about deformations.
But nothing else would be
No, I mean, you can talk, if you talk about tensor categories, for example, certain kind of fusion categories, its classification is unknown, but there are certainly many other cases. And it's a very interesting and largely not an understood business. I want to make one comment about Roman's comment. So actually, no, everything works in characteristic P, except that instead of quantum double, you should use the classical double of the Lie algebra. And then you can get U of G from U of B. Except that you will get also this mixed version between divided powers and without divided powers. Well, I have to think about, but at least at the level of Lie algebra, definitely you can get the whole Lie algebra from the half by taking the Drinfeld double of the Lie algebra. Oh, the dual is not, yes, of course. That's correct, yeah. So we will not get a Hopf algebra which is self-dual. Yeah. Other questions? Okay, thank you.